In this video, we'll discuss a couple of textbook examples that use some different software than what we'll demonstrate in our own class software, where we kind of do a walkthrough on how you do the analysis. So we'll just be looking at the examples and the results and practicing the interpretations. All right, so let's look at the kind of situation, and you can pause it and read through it if you'd like. But long story short, we're looking at the effect of consuming chocolate on cardiovascular health. Note again, this is a case where we're doing manipulation of a variable. So the types of chocolate we're manipulating: dark chocolate with milk, and then milk chocolate. And then we're also doing some fixing of variables, where we're fixing the potentially the age to a certain range, the weight to a certain range, and the BMI to a certain range. So we can see the data here, and again, this is a case where I really disagree with how the textbook has our data organized, because typically when we're analyzing this, we have 3 columns: DC, DC plus MK, and MC, and then going down the range is each of these different observations. If you're feeling good about this, you'll actually notice that this is a case where each of the observations does correspond with the same individual. We've only got 12 individuals. So individual 1 tried all 3 chocolates. Now, I will say this is actually a violation of independence. So this is typically not a good representation of the design. And if you come back to this video after we've gone through some of the stuff in later chapters, just acknowledge that yes, this is kind of a weird data set. But for right now, we're just not going to worry about it, and we're going to pretend that we didn't notice that. More specifically, we're just not going to worry about accounting for that, and we'll continue on with the analysis as if these were independent. So in this case, you can see from box plots of the data that it does look like dark chocolate is higher than the dark chocolate with milk and the milk chocolate. Now notice that this is a difference that we observe in our sample. And so the whole point of statistics is to go beyond the sample and to make conclusions about the population. So this is all well and good. Okay, dark chocolate has a higher antioxidant capacity than the other 2 options. The question that's left outstanding is, does this provide enough evidence to help us feel confident in a claim that dark chocolate has this effect in the population at large, or in outside of just this sample? So that's the question that's outstanding. And sometimes students get confused. They look at this graph and say, well, clearly dark chocolate's more. And the answer is yes in our sample. But the reason we're doing statistics isn't to tell us what we already know, that dark chocolate is more in our sample. The reason we do statistics, that we calculate that F statistic that we compare to an F distribution, is to get an idea of probability and confidence with which we can say this effect would happen outside of just our sample. This effect is an effect that would happen in the entire population of all the people. So here's our Minitab output. So we've got a lot going on here, but what I'm looking for when I look at output is I'm really looking for the ANOVA table breakdown. And again, that ANOVA table is pretty standard. We've got the different sources, we've got the degrees of freedom and the sums of squares, we've got the mean square and the F. And so actually I see that going on right at the top here. And what I'm looking at for my conclusion is this p-value. So in this p-value, I see that there is that the ANOVA test is statistically significant. So what does that mean? Think back to our null and alternative hypothesis. Statistically significant means that we reject the null in favor of the alternative. So the null hypothesis was that all of the means are the same. The alternative hypothesis was that at least one of the means is different. So given this p-value, we reject the null hypothesis in favor of the alternative, that at least one of the means is different. So we would say we have evidence that at least one of the mean levels of antioxidants is different for the chocolates. And again, from the graph, we kind of have an idea of which one that would be, but we don't know that for sure unless we run a statistical test, and we'll talk about those in a future chapter. Looking at this, there's a whole lot of other information that actually is I'm not going to really touch on right now. What I will touch on is that it can be nice. The box plots are nice. And you can see in Minitab, they kind of offer these low-tech graphic comparisons, kind of a classic graph from back in the day. But the other thing that can be really nice is just simple descriptive statistics of the means of each group. This can be really, really handy. So I see that the mean of the dark chocolate group is 116. The mean of dark chocolate and milk is 100.7, and the mean of milk chocolate is 100.18. So what I see here just from the means is just how much further up dark chocolate is than the dark chocolate plus milk and milk chocolate. And again, this doesn't actually mean anything standing alone, but taken with the fact that there was a statistically significant ANOVA, this lets me start to identify, okay, where is the difference? And we see the differences in dark chocolate. And not just that the difference is in dark chocolate, but that the difference is that the dark chocolate does seem to be larger than the other two. And again, this is reflected in our graphics. We'll talk about these kinds of comparisons later on, but we can see that there's confidence intervals comparing these different pieces to each other. So we have dark chocolate subtracted from the dark chocolate milk mix and milk chocolate, and then it has a comparison of these with a confidence interval for each of these, what are called pairwise comparisons. So that's where that is on the Minitab output. All right, let's look at another example. This one, a marketing example. And this is actually kind of cool because in a previous year, we actually had a class project. We were able to partner with a local organization and actually construct a design very similar to this, where we constructed a design for some different marketing materials to help determine, using an experimental design method, which marketing material was the most effective. And we kind of set up that study. So in this case, we've got a soft drink distributor who's looking at different displays. And so we're going to be looking at different displays in these different stores. Again, note how even here we have both variables that are manipulated and variables that are fixed. So our variable that's manipulated is the different displays. So we're going to have 3 different displays. And the variable that's fixed is the store size and the store type. So they identified 15 different stores of similar size and similar type. And actually a good other practice here is to realize that these 15 stores, these are our experimental units. So sometimes your experimental unit can be really big. Heck, we're talking about a store that may serve hundreds or thousands of people, and that's a single experimental unit. So in this case, we're going to have 15 experimental units to split between the 3 different design types. So here we have the different designs, and again, I'll make my note that typically we would have this in a transposed form where display design 1 has its own column, display design 2 has its own column, and display design 3 has its own column. I'll note that here, unlike with that other example, the components are unique. So observation 1 and display design 1 is a different store than observation 1 and display design 2, which is what we assume in the single one-way ANOVA. All right, so what ends up happening with this? Well, this output, J&P output, definitely looks a little bit different than what we saw previously. But again, what am I looking for? I'm looking for that traditional ANOVA table. So here, I see down here my analysis of variance. I've got model error, degrees of freedom, sums of squares, mean squares, F ratio. And actually what you notice here is that the probability, the p-value, isn't as its own column. This is kind of a weird format. But there it is. So because I know what I'm looking for, and because I know that I'm looking for this element, I know that this is a p-value. It's not just part of that column. And why is that? It's because I know what an ANOVA table is supposed to look like. I know that it's a pretty standard form. So here I see the model. Again, I've got 3 different design types. So 3 minus 1 gives me 2 degrees of freedom for the treatment. I would have 3 times the number of stores minus 1. So I've got 5 stores in each group. So 3 times 4 gives me 12. That's where the 0 degrees of freedom come in. And then the total number of degrees of freedom is capital N. The total number of stores, 15 minus 1. So I get my sums of squares components from those previous data, divide that by the degrees of freedom to get the mean squares, and then take the mean squares of the model divided by the mean squared error, and that's where that F ratio comes in, and we just plug it into software to calculate the p-value. In this case, I can see that the p-value is highly statistically significant. So what that says is there is evidence to determine that the display, one of the average outcomes for the display, is different than the other. So at least one of the means is different than the other. But I don't know which mean is different, and I don't know how different. So that's left outstanding, but at least one of the means is different. Again, there's a lot of other information here, but I will point out that the source is also listed down here. So if I had multiple independent variables, in this case I don't. So I just have display, which is part of that model. The sums of squares is the same, the F ratio is the same, and the p-value is going to be the same. But if I had more independent variables, let's say my model had 3 independent variables instead of just 1, on the JMP output, they would be displayed here, which is kind of nice because I could look at the significance of each independent variable next to each other. So continuing on, one of the nice things that I like about this is it does give the mean. So we kind of had a graph previously too. I prefer the box plots personally, but we also have the means here. So I can see that it's the mean of design 3 that's actually, excuse me, looks higher than the mean of design 1 or 2. And it looks like the mean of design 2 is higher than the mean of design 1, but I don't know that for sure. We'll talk about the specific comparisons here later on, but in this particular case, what we have is we're comparing the different means to each other. So we take the mean of one group and subtract the mean of the other. Now for me, I kind of, which one's subtracting what, I don't really know. So I kind of have to go back. I know that this is 1 and 1, this is 1 and 2. So is 1 subtracting 2 or is 2 subtracting 1? Well, I can go back here and I can say, all right, 1 is a lower number than 2, so this is negative, so the lower number is minusing the higher number. So the row minus the column is how this is going on. So this is the first level mean minus the second level mean. So we've got the standard error, the difference, and then confidence limits. And of course, using confidence intervals, we could actually do statistical hypothesis testing, where if 0 isn't in the confidence interval, then we know that these means are statistically significantly different from one another. Again, don't worry too much about this. We'll talk about this in a later video in this lecture set. This last one is a similar thing, but maybe a little easier to interpret. What happens is you put letters, sometimes multiple letters, for each factor level. And so how we interpret this is that any factor levels that share a letter, and again, sometimes there's multiple, but if they share any of the letters, then they're not different from one another. So here we see levels 1 and 2 share the letter B, and that indicates that both of these are in a particular group. They are not statistically different from one another. Level 3 has a different letter than either 1 or 2, so this is different than these bottom two. This is statistically significantly different from both level 2 and level 1. So this is a pretty cool way to get to run that interpretation and to get to visualize that. It kind of groups these together by letter. So level 3 is kind of in its own group higher up, and levels 2 and 1 are kind of in their own group together lower down, which is pretty cool. So this has been a discussion and interpretation of how I would go about reading through and interpreting a couple of different example problems, but this hopefully has also been a good way for how I can start to read through output from different types of software and what I look for when I'm reading output that I may have never seen before for a software I may have never used before, and how I can go about then still making the same kinds of interpretations that I would with any other software.